Every atom in your body was forged in the heart of a star that died billions of years ago, making you literally made of stardust. In the next 13 minutes, I'll show you exactly how the calcium in your bones, the iron in your blood, and the carbon in your DNA were all created through stellar alchemy. Imagine feeling connected to a cosmic lineage stretching back billions of years, a direct descendant of the universe's most powerful forces. This cosmic process is so improbable yet perfect that our existence becomes extraordinary. You'll discover not just the scientific mechanisms, but also the profound wonder behind each element that makes you you. Cosmic origins, the human-star connection. Take a moment and look at your hand. Flex your fingers. Feel your pulse. These seemingly ordinary body parts conceal an extraordinary origin story. That calcium strengthening your bones? It was forged in the fiery death of a massive star that exploded billions of years ago. The iron molecules carrying oxygen through your bloodstream originated in stellar cores under pressures and temperatures impossible to replicate on Earth. Your body is a cosmic assembly, a collection of elements with origins far beyond our planet. While we often think of ourselves as distinctly separate from the universe around us, the scientific reality tells us something profoundly different. We are made of the same stuff as stars, not in some poetic, metaphorical sense, but in absolute literal fact. The cosmic inventory of your body reveals an astonishing truth. Approximately 93% of your body mass consists of stardust, elements created through stellar nucleosynthesis. Only about 7%, mostly hydrogen, originated in the Big Bang. This makes us, in a very real sense, children of the stars. Each element in your body tells a chapter in this cosmic epic. Oxygen makes up about 65% of your body mass, followed by carbon at 18%, hydrogen at 10%, nitrogen at 3%, and calcium at 1.5%. Smaller amounts of phosphorus, potassium, sulfur, sodium, chlorine, and magnesium round out the major players, with trace amounts of elements like iron, zinc, copper, and iodine performing crucial biological functions despite their tiny proportions. Hydrogen stands as the protagonist in our cosmic narrative, the only element not forged in stars, but created in the Big Bang itself. The hydrogen atoms in your body's water molecules have existed unchanged since nearly the start of time itself. They've traveled through space, possibly been part of countless other structures before becoming part of you. But the other elements? They required stellar forges. The carbon forming the backbone of every organic molecule in your body was created when 3 helium nuclei fused in stellar cores through what astrophysicists call the triple alpha process. Without this precise nuclear reaction occurring in stars, carbon-based life, as we know it, couldn't exist. Your DNA, the blueprint of your physical existence, showcases this stellar assembly. Its backbone consists of carbon atoms, while the genetic information itself is encoded in the arrangement of nitrogen-containing bases. Both carbon and nitrogen were created through stellar nucleosynthesis, the process by which stars fuse lighter elements into heavier ones. The phosphorus connecting your DNA's backbone also originated in stars, albeit through different fusion pathways. The calcium in your bones followed a particularly remarkable path, like an intrepid traveler on a billion-year journey. It was synthesized in the final moments of a massive star's life, requiring temperatures over 100 million degrees Celsius. When that star exploded, calcium atoms scattered across space, drifting through the cosmos for eons before eventually becoming part of our solar system's molecular cloud, incorporating into Earth's forming crust, weathering out of rocks, dissolving in water, being absorbed by plants, consumed by animals, and finally integrating into your skeletal structure. Iron tells another compelling story, the unsung hero in a cosmic relay race. The iron atoms in your hemoglobin molecules, carrying oxygen to your cells, could only have been created in the cores of massive stars just before they exploded as supernovae. Iron represents a turning point in stellar fusion. It's the last element that can be created while releasing energy. Trying to fuse iron actually consumes energy which is why iron accumulation in stellar cores leads to supernova explosions. If we could visualize the cosmic origins of each atom in your body, you would appear as a constellation of elements from different stellar sources. Your right hand might contain atoms from different stars than your left. Some may have cycled through multiple stellar generations before becoming part of you. This cosmic perspective transforms even the most mundane aspects of human existence. That morning stretch, you're flexing stellar material. The breath you just took, you inhaled atoms that once existed in the cores of stars. The thoughts forming in your mind right now are electrical signals passing between cells constructed from stellar elements. Our bodies represent the culmination of an almost unfathomable journey. These atoms traveled from stellar cores through the vacuum of space, became part of a forming solar system, concentrated in Earth's crust, were taken up by plants, moved through food chains, and eventually became incorporated into human tissues through biological processes refined over millions of years of evolution. What's particularly mind-bending is that these elements continued existing long after their parent stars died. The atoms in your body are likely billions of years old, having been recycled through countless cosmic and geological processes before becoming part of you. They'll continue existing long after your body returns them to Earth's biochemical cycles. This perspective radically changes our relationship with the cosmos. We are not separate observers of the universe. We are the universe observing itself. The same physical processes that created stars and planets assembled the biological structures that allow us to comprehend those very processes. There's an elegant circular nature to this realization. Stellar nurseries, where stars are born. This circular relationship between ourselves and the cosmos begins in a place few would expect. Massive clouds of gas and dust that appear static and unchanging to the casual observer. Yet inside these molecular clouds, a battle between gravity and turbulence creates the perfect conditions for stellar birth, without which none of the elements essential to life would exist. These stellar nurseries are among the most extraordinary environments in our universe. Molecular clouds stretch across hundreds of light years of interstellar space, containing enough raw material to form millions of stars. Despite their immense size and importance, these cosmic incubators exist in a state that contradicts our intuition about star formation. They're incredibly cold, with temperatures hovering just a few degrees above absolute zero, the lowest temperature theoretically possible. The composition of these clouds tells us much about the universe's evolution. They consist primarily of molecular hydrogen atoms that have paired up to form H2 molecules, along with smaller amounts of other molecules like methanol and water. Scattered throughout this gaseous mixture are tiny dust grains, some reaching up to a few millimeters in size. These dust particles play a crucial role in the star formation process by allowing the gas to cool efficiently and providing surfaces where molecules can form. What makes these clouds particularly fascinating is the contrast between their frigid temperatures and the blazing infernos they eventually produce. How does something so cold give birth to objects as hot as stars? The answer lies in the delicate balance of forces within these clouds. From a distance, molecular clouds might appear tranquil, but they're actually in constant motion. Turbulent flows cause gas and dust to swirl and collide, creating regions of varying density throughout the cloud. These density fluctuations become the seeds of future star systems. In areas where matter becomes slightly more concentrated, gravity begins to exert a stronger pull on the surrounding material. This is where the true drama begins. Once a region reaches a critical density, gravity takes over and initiates a process that's difficult to stop. As more material falls inward, the density increases further, strengthening gravity's grip and pulling in even more gas and dust. What starts as a subtle variation in the cloud quickly develops into a runaway process of gravitational collapse. As this collapse continues, something remarkable happens. The gravitational potential energy of the falling material converts to thermal energy. Simply put, the compression generates heat. while the outer regions of these collapsing clouds remain frigid at around 10 Kelvin. The innermost regions begin to warm dramatically, eventually reaching temperatures of about 300 Kelvin, comparable to room temperature on Earth. This temperature gradient creates pressure that would normally counteract gravity, but in these early stages, the cloud continues to contract. The quiet darkness of the molecular cloud gradually gives way to a storm of creation. Over approximately 50,000 years, this core contracts further from roughly 10,000 astronomical units to about 1,000 Australian dollars across. These timescales might seem long by human standards, but in cosmic terms, they represent a rapid transformation. An interesting phenomenon occurs during this contraction. Imagine a figure skater spinning on ice. As they pull their arms close to their body, they spin faster and faster. The same principle applies to our stellar nursery. The rotation of the original cloud, however slow it might be, becomes amplified through the collapse. This conservation of angular momentum causes the collapsing cloud to flatten into a disk around the central dense region. The material doesn't simply fall straight in, but spirals toward the center, forming a protostar at the core, surrounded by a protoplanetary disk. This disk structure is critical for both the developing star and future planets. As material in the disk continues to spiral inward, feeding the growing protostar, the increasing density and temperature at the center create conditions unlike anything else in the cloud. Meanwhile, some of the infalling material gets channeled along the rotation axis and ejected outward as high-speed jets from the protostar's poles, a phenomenon that helps regulate the star formation process. What's particularly fascinating about this stage is the balance between different physical forces. Gravity pulls material inward, rotation creates the disk structure, and the gradually increasing pressure and temperature at the center will eventually provide the counterforce needed to prevent complete collapse. It's a cosmic ballet choreographed by fundamental physics. As dramatic as this transformation is, the most profound aspect might be what it means for the universe's chemical evolution. The earliest universe that emerged from the Big Bang was composed almost entirely of hydrogen and helium, the two simplest elements. In such a universe, complex life, as we know, it would be impossible. The absence of elements like carbon, oxygen, and nitrogen meant that the intricate molecular machinery of life couldn't exist. This is where the profound importance of star formation becomes clear. These molecular clouds represent the beginning of a cosmic alchemy that transforms the simplest elements into the full spectrum of building blocks needed for complex chemistry and eventually life. They are the first stage in a process that will ultimately create every element heavier than helium, including those essential to our existence. The stark simplicity of the early universe, consisting of just hydrogen and helium with traces of lithium, made it completely inhospitable to complex chemistry. Stars are the only natural factories capable of producing these heavier elements, making them essential creators of complexity. As these protostars continue to contract under their own gravity, the pressure and temperature in their cores climb ever higher. The once frigid molecular cloud material transforms dramatically as it approaches the center of the forming star. From the near absolute zero temperatures of the original cloud, the core heats to thousands, then tens of thousands, and eventually millions of degrees. This transformation from frigid molecular cloud to hot protostar represents one of the most extreme physical metamorphoses in nature. Looking up at the stars, we're witnessing the end result of this incredible journey, a journey that will eventually produce the very atoms in our bodies. Nuclear fusion, the stellar forge, ignites. The extreme compression at the protostar's core creates conditions that exist nowhere else in nature. A cosmic pressure cooker where atoms move so violently they can accomplish what seems physically impossible. Without a quantum mechanical loophole in the laws of physics, stars couldn't exist, and neither would we. When a protostar's core reaches temperatures of several million degrees Celsius, it crosses a remarkable threshold. At this pivotal moment, hydrogen nuclei, which normally repel each other due to their positive charges, are forced so close together by the extreme pressure and temperature that they can fuse into helium. This transformation represents one of the most significant moments in astrophysics, the birth of a true star. The immense gravitational forces pressing inward create pressures that compress hydrogen atoms to densities millions of times greater than anything we experience on Earth. Under such extreme conditions, the laws of physics bend in fascinating ways. The fusion process shouldn't technically be possible at the temperatures found in stellar cores based on classical physics alone. The temperatures required for hydrogen nuclei to overcome their electrostatic repulsion would typically be far higher than what we observe in stars like our Sun. Here, quantum mechanics introduces a crucial mechanism to our cosmic story. Through quantum tunneling, hydrogen nuclei can essentially cheat the classical laws of physics. Rather than needing enough energy to completely overcome the repulsive barrier between them, quantum tunneling allows particles to occasionally pass through this barrier, even when they technically don't have sufficient energy to do so. It's as if two magnets with the same pole suddenly overlap through a hidden dimension and merge together. This quantum loophole dramatically reduces the temperature threshold needed for fusion to occur, making stars, and by extension, life, possible throughout the universe. When hydrogen nuclei fuse into helium, a small amount of mass disappears in the process. The resulting helium nucleus weighs slightly less than the sum of the original hydrogen nuclei. This tiny mass difference converts directly into energy according to Einstein's famous equation, E equals mc squared. Though the mass difference is minuscule, less than 1% of the original mass, the energy released is enormous because it's multiplied by c superscript 2, the speed of light squared, roughly 90 billion kilometers squared per second squared. This explains how stars can produce such tremendous energy from relatively small amounts of matter. This energy creates photons that begin journeying outward from the star's core, bouncing around inside the star for thousands or even millions of years before eventually reaching the surface and radiating into space. The outward pressure from this energy production finally halts the gravitational collapse that has been ongoing since the molecular cloud first began to contract. Where once there was a collapsing ball of gas growing ever hotter and denser, now stands a balanced system, a true star. The protostar's chaotic compression transforms into a precisely regulated fusion reactor as the star reaches hydrostatic equilibrium, a perfect balance between the inward pull of gravity and the outward push of fusion pressure. This balance point represents the official birth of a main sequence star, the stable phase where stars like our Sun spend the majority of their lives. This balancing act is remarkably self-regulating. If fusion temporarily slows, gravity compresses the core further, raising temperature and pressure, automatically boosting the fusion rate. If fusion runs too hot, increased pressure expands the core slightly, cooling it and reducing the fusion rate. This self-regulation explains how stars remain stable for incredibly long time frames, millions or billions of years. The primary fusion process in most stars involves the proton-proton chain, converting hydrogen nuclei into helium, through a series of intermediate steps. In more massive stars with hotter cores, above approximately 17 million degrees Celsius, the CNO cycle dominates, using carbon, nitrogen, and oxygen as catalysts. Our Sun, at 15 million degrees, primarily uses the proton-proton chain. This cosmic pressure cooker at the heart of every star connects directly to our daily lives. Every photon warming Earth's surface, every unit of energy in our food, every fossil fuel we burn, all ultimately derive from these nuclear fusion reactions. The energy released travels 93 million miles through space to reach us, linking our everyday experiences to nuclear processes happening in our parent star. Understanding fusion gives us insight not just into energy production, but also element creation. While initial fusion primarily creates helium, This process sets the stage for more complex nuclear reactions occurring later in a star's life. Through successive fusion of increasingly heavier elements, stars create the diverse atomic building blocks that eventually form planets and living organisms. The moment of stellar birth, when fusion ignites and hydrostatic equilibrium establishes, marks the beginning of element creation in the universe. Before stars, the cosmos consisted almost entirely of hydrogen and helium from the Big Bang. Stars transform this simple inventory into the rich diversity of elements we see today. The equilibrium defining a main sequence star is both physical and temporal. This stable phase lasts for approximately 90% of a star's lifetime, about 10 billion years for our Sun, with roughly 5 billion years already elapsed. During this extended period, the star maintains remarkably consistent properties, providing the stable energy output that has allowed life to evolve on Earth. Stellar mass, the destiny determiner. That stable 10 billion year lifespan our Sun enjoys represents just one possible stellar destiny among many. Imagine stars as cosmic alchemists, each with different capabilities based solely on their size. Some can only create the universe's simplest elements, while others forge the exotic materials that make up our world. What makes the difference between these cosmic creators? A single factor that determines everything: mass. When a star forms from the gravitational collapse of gas and dust, its initial mass becomes the master variable that programs its entire life story. Mass acts as a cosmic scale, tipping dramatically toward either longevity or intensity, depending on a star's heft. This fundamental parameter dictates everything from internal temperature and pressure to evolutionary pathway and ultimate fate. Stellar mass functions as a cosmic DNA sequence containing all the instructions for what a star will become and what chemical contributions it will make to the universe. The range of stellar masses is staggering. At the lower end, red dwarf stars can form with as little as 0.08 times the mass of our Sun. Any less, and there isn't enough gravitational pressure to ignite fusion at all. At the upper extreme, supergiant stars can contain up to 200 solar masses, though these cosmic behemoths are exceedingly rare. Between these extremes lies a spectrum of stellar types, each with its own characteristic life cycle and nucleosynthetic potential. What's particularly fascinating is how dramatically a star's mass affects its lifespan through a counterintuitive relationship. The more massive a star, the shorter its life. A red dwarf with about 0.1 solar masses burns steadily for up to 10 trillion years, outlasting the current age of the universe by a factor of 700. Meanwhile, those dazzling blue supergiants that shine with the brilliance of a million suns exhaust their nuclear fuel in mere millions of years, sometimes lasting only a few 100,000 years before their spectacular deaths. This inverse relationship between mass and longevity stems directly from the physics of stellar cores. More massive stars must generate greater outward pressure to counterbalance their immense gravitational pull. This requires much higher core temperatures and correspondingly faster fusion rates. While our Sun's core operates at about 15 million degrees Celsius, a star with 15 times the Sun's mass maintains core temperatures above 35 million degrees. These extreme conditions accelerate nuclear reactions exponentially, causing massive stars to burn through their fuel supply at a dramatically faster pace. The temperature differences between stellar cores create a fascinating cascade of consequences. When a star's core reaches specific temperature thresholds, new fusion pathways become possible. For instance, our Sun's modest core temperature allows it to fuse hydrogen into helium, but it will never get hot enough to fuse carbon. In contrast, those short-lived massive stars achieve the necessary 600 million degrees to fuse carbon into neon, magnesium, and other elements. This temperature-dependent progression creates a direct link between a star's mass and the chemical elements it can synthesize. The smallest stars, the red dwarfs, will spend trillions of years converting hydrogen to helium and nothing more. Medium-mass stars like our Sun eventually develop hot enough cores to fuse helium into carbon and oxygen, creating the essential building blocks for organic chemistry. But only the most massive stars, those with at least 8 times the mass of our Sun, achieve the blistering core temperatures needed to create the full spectrum of naturally occurring elements up through iron. Consider the efficiency differences between stellar classes. If our Sun were just 3 times more massive, its hydrogen-burning lifespan would shrink from 10 billion years to about 500 million years, a staggering 95% reduction in longevity. This extreme compression of the evolutionary timeline means that massive stars race through their developmental stages at a breathtaking pace, sometimes transitioning between major fusion phases in mere thousands of years rather than billions. The mass of a star determines which elements it can create and how those elements will be distributed into space. Low-mass stars like our Sun will eventually shed their outer layers gently as planetary nebulae, releasing carbon and oxygen to the cosmos while leaving behind dense white dwarf remnants. In dramatic contrast, high-mass stars conclude their lives with supernova explosions that violently disperse their complex elemental inventory across interstellar space, while leaving behind exotic remnants like neutron stars or black holes. The universe's elemental enrichment depends on this diversity of stellar types. If all stars had the Sun's mass, the cosmos would be severely depleted of elements heavier than oxygen. The periodic table's upper regions, including metals like copper and zinc, as well as heavier elements such as iodine and gold, require the extreme conditions found only in massive stars and their explosive deaths. This cosmic specialization creates a kind of stellar division of labor, with different mass classes contributing different elements to the universal inventory. For cosmic perspective, consider the supergiants, those immense stars with 8 to 200 solar masses. Despite comprising less than 1% of all stars, these cosmic giants produce nearly all the universe's heaviest elements. When you look at a massive red supergiant like Betelgeuse, with its surface temperature below 4,100 K and a diameter that would extend beyond Jupiter's orbit if placed in our solar system, you're observing a stellar chemistry lab creating elements that will eventually seed future generations of stars, planets, and potentially life. This stellar mass element connection creates a profound chemical evolution across cosmic time. The earliest stars formed from the primordial hydrogen and helium left over from the Big Bang. When these first-generation stars died, particularly the massive ones, they enriched the cosmos with the first heavy elements. Each subsequent generation of stars formed from increasingly element-rich gas clouds, allowing the formation of more complex chemical systems, including stellar rocky planets and eventually biological organisms. Those element-rich gas clouds that seed new star systems don't appear by magic. They're the product of stellar alchemy occurring inside aging stars. What happens when a star exhausts its primary hydrogen fuel? Rather than simply dying, it transforms into a multi-layered element-building machine, where different fusion reactions occur simultaneously in distinct zones, each producing different elements on the periodic table. As stars age, they undergo remarkable transformations that completely restructure their interiors. Once a star depletes the hydrogen in its core, gravitational forces take over, causing the core to contract. This contraction generates tremendous heat. The temperature rises dramatically, setting the stage for the next phase of fusion. Meanwhile, the star's outer layers expand and cool in response, causing the star to swell dramatically in size, becoming a red giant or red supergiant, depending on its initial mass. This transformation creates ideal conditions for building progressively heavier elements. The increased core temperature enables helium nuclei to overcome their mutual repulsion and fuse together. For stars like our Sun, this phase marks a critical transition, the beginning of helium fusion that will eventually create carbon, one of life's essential building blocks. Peer inside an aging star and you discover a structure resembling an onion, with distinct layers where different nuclear reactions occur simultaneously. Each concentric shell maintains specific temperature and pressure conditions that enable particular fusion reactions. The innermost core might be fusing helium into carbon, while surrounding layers continue hydrogen fusion. In more massive stars, this layered architecture becomes even more complex, with multiple fusion processes operating in concert, each shell a specialized workshop in this cosmic element factory. The triple alpha process represents one of the most crucial reactions in stellar evolution. This process occurs when 3 helium nuclei, alpha particles, fuse to form a carbon nucleus. The name comes from the fact that helium nuclei are also known as alpha particles in nuclear physics. What makes this process remarkable is that it requires a precise resonance energy state discovered by physicist Fred Hoyle, who predicted its existence based on the observed abundance of carbon in the universe. Without this specific resonance, a quantum mechanical phenomenon where the energy levels align just right, carbon would be extremely rare in the universe, and carbon-based life would be impossible. The triple alpha process occurs at temperatures around 100 million degrees Celsius and represents how precisely the fundamental constants of physics seem tuned to allow for life's essential elements. Once carbon forms in the star's interior, it can capture additional helium nuclei to form oxygen, another element vital for life as we know it. This carbon-to-oxygen transformation happens in the same stellar zones where the triple alpha process occurs, creating a rich mixture of these biologically essential elements. In stars more massive than our Sun, the temperature and pressure reach even higher thresholds, enabling further fusion steps. Carbon nuclei fuse to form neon and sodium. Neon and oxygen combine to create magnesium. Successive reactions produce silicon, sulfur, and eventually culminate with iron. Each step requires dramatically higher temperatures and produces less energy than the previous fusion stage. This progression through increasingly heavy elements follows a pattern dictated by nuclear physics. Elements with even numbers of protons and neutrons tend to be more stable and abundant. This pattern explains why certain elements are more common in the universe. They represent the stable points in stellar nucleosynthesis. The energy dynamics change dramatically as stars evolve. In the main sequence phase, hydrogen fusion generates abundant energy, creating outward pressure that balances against gravity. But as stars forge heavier elements, the energy yield from fusion diminishes. The fusion of silicon into iron marks a pivotal moment. Iron represents a fusion dead end because of its position at the peak of the nuclear binding energy curve. Any attempt to fuse iron nuclei together requires energy input rather than releasing energy. This fundamentally changes the star's energy balance. When a massive star develops an iron core, it's burning the last viable nuclear fuel. With no energy production to counter gravity, the core becomes vulnerable to collapse. Different stellar types contribute unique elements to the cosmic inventory. Medium-mass stars like our Sun primarily produce carbon and oxygen through helium fusion. Their cores never reach temperatures needed to create heavier elements. Only the most massive stars, those at least 8 times the Sun's mass, can forge elements up through iron. The timing of these fusion stages varies dramatically with stellar mass. While our Sun will spend billions of years fusing hydrogen, then hundreds of millions fusing helium, a star 20 times more massive races through these same stages in just millions of years. When such massive stars reach silicon fusion, the process creating iron, they're in their final days or hours. The silicon-to-iron conversion might last mere days before catastrophic collapse. This creates a profound specialization among stars. Low-mass stars serve as hydrogen converters and helium stockpilers. Medium-mass stars like our Sun are carbon and oxygen factories. Only the most massive stars, living brief but brilliant lives, create the full range of elements up through iron. The CNO cycle represents another crucial fusion pathway in massive stars. Unlike the proton-proton chain powering our Sun, the CNO cycle uses carbon, nitrogen, and oxygen as catalysts to facilitate hydrogen fusion. These elements cycle through different isotopes while helping convert hydrogen to helium. The CNO cycle becomes dominant at higher temperatures, making it the primary energy source in stars more massive than about 1.3 times our Sun. For stars like our Sun, carbon formation occurs during the asymptotic giant branch phase, a late evolutionary stage where helium fusion occurs in shells around the core. During this phase, the star becomes highly unstable, experiencing pulses of energy release and ejecting shells of material into space. These ejected shells, enriched with newly formed carbon and oxygen, contribute directly to the interstellar medium, each element a note in the symphony of cosmic creation. Stellar deaths, explosive element factories. These ejected shells from sun-like stars represent just one way stellar material returns to the cosmos. But what about the elements heavier than iron that make up your gold jewelry or smartphone components? The periodic table's heaviest elements require a cosmic forge far more violent than gentle stellar winds. They demand the extraordinary conditions only found in the final, explosive moments of a star's life. The dramatic ending of a stellar story is fundamentally determined by the star's birth weight. While modest stars similar to our Sun experience relatively peaceful transitions into retirement, shedding their outer layers to create beautiful planetary nebulae, stars exceeding 8 solar masses face a cataclysmic finale. These massive stellar beings conclude their existence through supernova explosions, the most energetic events humans have ever witnessed in the cosmos. Within massive stars, the accumulation of iron in the core functions as a ticking doomsday clock. Unlike lighter elements that release energy when fused, iron consumes energy during fusion attempts. This fundamental shift disrupts the star's delicate balance. When fusion can no longer generate the outward pressure needed to counterbalance gravity's relentless inward pull, the star faces an existential crisis. What follows happens with breathtaking speed. The iron core collapses under its own weight at approximately 1/4 the speed of light. This implosion transforms the core from Earth-sized to an ultra-dense ball merely 20 kilometers across in less than a second. The resulting pressure forces electrons to combine with protons, creating neutrons and releasing neutrinos that carry away enormous energy. As the outer layers slam into this incompressible neutron core, they create a rebounding shockwave that powers the explosive ejection of the star's material into space. A cosmic phoenix moment where destruction leads to creation. Have you ever wondered how your gold jewelry came into being? The James Webb Space Telescope has captured this creation process, preserved in the supernova remnant Cassiopeia A. The remnant appears as bright orange and light pink clumps that make up the inner shell, where Webb's razor-sharp view can detect the tiniest knots of gas, comprised of sulfur, oxygen, argon, and neon from the star itself. The outer regions resemble smoke from a campfire, where the blast wave continues ramming into surrounding material. During these explosive moments, the extreme temperatures and neutron-rich environment enable the R process, rapid neutron capture. In this extraordinary environment, atomic nuclei capture neutrons faster than they can decay, building heavier elements in seconds. This cosmic alchemy creates approximately half of all elements heavier than iron, including gold, thorium, uranium, and plutonium. The supernova's core, if sufficient mass remains, survives this cataclysm as an incredibly dense neutron star, essentially an atomic nucleus the size of a city. With approximately 1.5 times our Sun's mass compressed into a sphere only 20 kilometers across, a neutron star contains matter so dense that a teaspoonful would weigh billions of tons on Earth. Some massive star remnants collapse even further, forming black holes, objects so gravitationally powerful that not even light can escape. These stellar remnants themselves can create additional heavy elements when they interact. When two neutron stars spiral together and merge, they produce an even more extreme environment for the R process. These rare events likely generate most of the gold and platinum found throughout the universe. Type Ia Supernovae represent another explosive source of cosmic elements. These occur in binary star systems where a white dwarf accumulates material from a companion. If the white dwarf's mass exceeds 1.44 times the sun's mass, the Chandrasekhar limit, it explodes as a type Ia supernova. These remarkably consistent explosions serve astronomers as standard candles for measuring cosmic distances. Recent observations of supernova SN 2023X in the Pinwheel Galaxy provided unprecedented early measurements of polarized light, revealing the evolving shape of this stellar explosion. Meanwhile, supernova 2023 UFS, the most metal-poor stellar explosion ever recorded, offers a glimpse of conditions resembling the early universe, when the first generation of stars were forming and dying. These ancient stellar explosions help astronomers understand how the earliest stars seeded the universe with the first heavy elements. These primordial supernovae initiated the process of metal enrichment that eventually made rocky planets and life possible. Look around you. The material world contains countless elements that formed through these violent stellar deaths. The uranium powering nuclear plants, the gold in wedding rings, the silver in electronic devices, the iodine essential for thyroid function, all required supernova explosions or neutron star mergers for their creation. After being synthesized in stellar explosions, these heavy elements drifted through interstellar space, eventually becoming incorporated into the molecular cloud that formed our solar system. As planets coalesced from this enriched material, the heaviest elements became concentrated in rocky worlds like Earth. The immense energy of these stellar explosions explains why some elements are extraordinarily rare. Gold's scarcity directly reflects the uncommon conditions required for its creation. All the gold ever mined on Earth would fit into a cube roughly 21 meters on each side, a testament to how exceptional the R process truly is. These violent stellar deaths also trigger the formation of new stars. The expanding shells of supernova remnants compress surrounding gas clouds, initiating gravitational collapse that leads to new stellar births. This cosmic cycle ensures that each generation of stars enriches the universe with increasingly diverse elements. The Webb telescope's image of Cassiopeia also revealed baby Cass, a light echo where light from the star's long-ago explosion has reached and is warming distant dust, which is glowing as it cools down. This ghostly offspring is located about 170 light-years behind the main remnant, demonstrating how a single explosion can influence vast regions of space. Cosmic distribution, elements journey through space. While that cosmic light echo we observed 170 light-years behind Cassiopeia, it demonstrates the far-reaching impact of a single stellar explosion. It represents just the beginning of an element's epic journey. Between a star's violent death and the eventual formation of planets, like Earth stretches an odyssey spanning thousands of light-years and hundreds of millions of years. A voyage that transforms stellar debris into the fundamental building blocks of life itself. This cosmic migration unfolds within the interstellar medium, the seemingly empty space between stars that's actually a vast tapestry woven from the remnants of stellar evolution. This medium serves as both cosmic highway and mixing bowl for the elements essential to our existence. What appears as emptiness to our eyes is actually an intricate environment where the past and future of matter continually intersect. When supernova remnants expand outward, they propel shells of gas and debris at tremendous velocities, colliding with and sweeping up existing interstellar material. These high-speed interactions generate powerful shock waves that heat and compress surrounding gas and dust. The newly synthesized heavy elements, calcium, iron, and others, thoroughly mix with the ambient material, gradually enriching the galaxy's elemental inventory with each explosive event. Stars disperse their manufactured elements through multiple channels. Throughout their lifetimes, stars continuously release material through stellar winds, streams of particles ejected from their surfaces. While less dramatic than supernovae, These winds provide a steady mechanism for distributing elements. Aging red giants notably shed their outer layers, releasing their nuclear processed materials long before their final demise. The distribution of elements throughout a galaxy depends on several cosmic mixing processes working in concert. Turbulence within the interstellar medium, caused by stellar winds and explosions, acts like a cosmic spoon stirring cream into coffee, preventing elements from remaining concentrated in small regions. The galaxy's rotation enhances this mixing. Different regions orbit the galactic center at varying speeds, creating a shearing effect that stretches and intertwines regions of interstellar gas, similar to how different layers of river water move at different speeds, blending sediments from various sources. This differential rotation causes clouds of gas enriched with different elements to intersect and blend over millions of years. Meanwhile, shock waves generated by stellar explosions compress and heat the interstellar medium, further promoting distribution of diverse elements. This enriched material eventually gathers into molecular clouds, stellar nurseries spanning hundreds of light years that contain the accumulated products of countless stellar deaths. When gravitational instabilities cause regions within these clouds to collapse, they form new stars and planetary systems that inherit all the elemental wealth of their galactic neighborhood. The cycle creates an increasing complexity timeline. The first stars formed after the Big Bang contained almost exclusively hydrogen and helium. As these primitive stars lived and died, they created the first batches of heavier elements and released them into space. Subsequent generations of stars formed from this enriched material, incorporated these new elements, created even heavier ones, and then returned an even more diverse mixture to the cosmos. Our solar system represents a relatively recent chapter in this ongoing saga. The molecular cloud that collapsed to form our sun and planets was already enriched by multiple generations of stellar processing. The specific mixture of elements in our solar system reflects the cumulative history of all the stars that lived and died in our galactic neighborhood before the sun's birth 4.6 billion years ago. Earth and other rocky planets contain substantial amounts of elements that require advanced stellar processes, elements synthesized only in later generations of stars that incorporated the products of their predecessors. Radioactive isotopes found in meteorites suggest that our solar system's formation was likely triggered by a nearby supernova. The shock wave compressed part of a molecular cloud, initiating the collapse that would become our solar system while injecting freshly created radioactive elements whose decay products we measure in meteorites today. Earth emerges as the product of a galactic recycling program billions of years in the making. The calcium in our bones and the iron in our blood traveled from the hearts of ancient stars through the vast interstellar medium into the collapsing cloud that formed our solar system, and finally into our planet where they became incorporated into living organisms. Supernova 2023 F's, an unusually metal-poor stellar explosion, offers a unique window into this complex history. By studying such metal-poor environments, astronomers glimpse conditions similar to those in the early universe, when stellar processing had just begun to enrich the cosmos with heavy elements. These observations help us understand how the first generations of stars seeded the universe with essential ingredients that would eventually enable planets and life to form. What's remarkable about this process is its inefficiency. Most elements ejected by dying stars will never become part of a planet or living organism. Most material remains diffuse, perhaps to be incorporated into new stars billions of years in the future. The elements that ended up in Earth represent a tiny fraction of all matter processed through stars. Yet they were sufficient to create a world of incredible chemical and biological complexity. The journey from stellar core to human body spans tens of thousands of light years across our galaxy and billions of years of time. A cosmic river that eventually feeds new worlds. The atoms in your body have traversed interstellar space, participated in the birth of our solar system, been incorporated into Earth's crust, and cycled through countless geological and chemical processes before becoming part of a living organism. From stardust to life, the biological connection. The atoms in your body completed an extraordinary cosmic journey to reach Earth, but their arrival on our planet was far from the end of their story. On early Earth, a hostile world of volcanic eruptions, meteorite impacts, and harsh ultraviolet radiation. These stellar elements faced a seemingly impossible challenge, organizing themselves into the intricate molecular structures that would eventually become living cells. When our planet formed approximately 4.5 billion years ago, it presented a starkly different environment from the life-sustaining world we know today. The primordial atmosphere lacked the oxygen we now breathe freely. Instead, the skies were filled with gases that would be toxic to modern life forms. The absence of our protective ozone layer meant that intense ultraviolet radiation from the sun bombarded the surface unfiltered, breaking apart complex molecules in exposed areas. This harsh radiation provided energy necessary for chemical reactions while simultaneously destroying their products. Imagine standing on the shore of an ancient sea under skies crackling with electrical storms. Each lightning bolt striking the water catalyzed fleeting chemical reactions in the primordial soup. Yet in sheltered places, deep ocean waters, beneath rocky outcrops, within porous structures near hydrothermal vents, delicate chemical processes unfolded protected from the sun's destructive power, like tender seedlings finding refuge in the crevices of rocks after a violent storm. The planet's geological processes became crucial in this chemical evolution. Volcanic activity released gases and minerals from Earth's interior, cycling elements throughout the developing crust. Volcanoes continuously erupted, releasing carbon dioxide and water vapor into the atmosphere, while ejecting minerals containing phosphorus, sulfur, and various metals, critical elements for future life. Meanwhile, the cycling of water through evaporation and precipitation created concentration gradients, gathering specific elements in various environments. As water accumulated in the early oceans, it became a dynamic chemical laboratory. The unique properties of water, its polarity, ability to form hydrogen bonds, and capacity as a solvent, made it the perfect medium for complex chemistry. In these aqueous environments, simple molecules began interacting in increasingly complex ways. Energy sources abounded. Lightning strikes, ultraviolet radiation penetrating shallow waters, and intense heat and minerals emerging from hydrothermal vents on the ocean floor. In these diverse settings, prebiotic chemistry began transforming simple inorganic compounds into increasingly complex organic molecules. The unique bonding properties of carbon proved especially significant. Carbon can form stable bonds with itself and many other elements, creating chains, rings, and three-dimensional structures of remarkable complexity. This versatility allowed carbon to serve as the backbone for amino acids, nucleotides, and fatty acids, fundamental building blocks for proteins, DNA, and cell membranes. Carbon's ability to form these complex structures resulted directly from its formation through the triple alpha process in aging stars, creating the perfect element with precisely the right properties to enable complex life. Across early Earth, these organic building blocks concentrated and combined. Along mineral surfaces where clay particles provided structural templates, within tiny pores of hydrothermal vent systems, or in shallow tide pools experiencing cycles of wetting and drying. Increasingly complex molecules formed. Amino acids linked into short protein-like chains. Nucleotides arranged themselves into sequences resembling primitive genetic material. Fatty acids spontaneously formed membrane-like structures that could separate inside from outside, a fundamental requirement for cellular life. The timeline from Earth formation to the first appearance of life spans several 100 million years. Geological evidence suggests liquid water existed on Earth as early as 4.4 billion years ago, making chemical evolution possible from nearly the beginning. The earliest fossil evidence of life, in the form of microbial communities, dates back approximately 3.5 billion years, leaving a window of nearly a billion years during which the miraculous transition from chemistry to biology occurred. When the first truly living organisms emerged, they possessed a remarkable ability. They could selectively incorporate elements from their environment through primitive metabolic processes. This selection was driven by the specific chemical properties of each element. Early life developed mechanisms to concentrate certain elements while excluding others, creating internal environments with element compositions vastly different from the surrounding world. As life evolved over billions of years, these selective processes became increasingly sophisticated. Different elements were incorporated into biological systems based on their unique chemical properties. Calcium became essential for structural support in shells and eventually bones. Iron's capacity to bind oxygen made it perfect for transporting this essential gas in blood. Phosphorus became central to DNA structure and cellular energy transfer. The evolutionary pressures continuously refined these element selections. Through countless generations, organisms evolved more efficient ways to acquire, concentrate, and utilize specific elements from their surroundings. Modern biology's precisely optimized relationship with the periodic table began in the hearts of stars, continued through cosmic distribution, and was refined through billions of years of evolution. The human body represents the culmination of this long process of element selection. When examining the distribution of elements in human tissues, you find highly specialized concentrations. Phosphorus concentrates in DNA and energy transfer molecules. Zinc and copper accumulate in enzymes where their specific properties catalyze crucial reactions. Iodine gathers in the thyroid gland to regulate metabolism. Biological systems can distinguish between chemically similar elements, incorporating one while excluding another. Your body readily absorbs potassium, but carefully regulates sodium levels. It accumulates zinc while rejecting the chemically similar but toxic cadmium. These selective mechanisms represent billions of years of evolutionary refinement in our relationship with the elements created in stellar furnaces. The journey from stellar elements to living systems required this 4.5 billion year process of geological concentration, chemical evolution, and biological incorporation, a cosmic recycling program of extraordinary ongoing precision stellar connection. Beauty. The astronomical journey that brought elements from dying stars into your body doesn't end with your last breath. What if I told you that the atoms making up your cells right now have already been part of countless other organisms throughout Earth's history and will continue their journey long after you're gone? How does it feel to be part of a timeless cycle that extends far beyond your individual existence? The elements that constitute the human body exist in a constant state of flux, cycling through Earth's interconnected systems in an endless dance of transformation. This movement follows precise patterns known as biogeochemical cycles, nature's recycling systems that govern how elements like carbon, nitrogen, and phosphorus flow through the living and non-living parts of our planet. These cycles ensure that the building blocks of life remain available for future generations of organisms, continuing a process that began billions of years ago in the hearts of ancient stars. Consider carbon, the backbone of all life on Earth. Right now, this element forms the structure of your DNA, proteins, and cell membranes. But after death, microorganisms break down these complex organic structures during decomposition, releasing carbon in simpler forms that return to the soil and atmosphere. Plants then absorb this carbon dioxide through photosynthesis, incorporating it into new organic molecules. Animals consume these plants, and the cycle continues. The same carbon atoms passing from organism to organism in an unbroken chain stretching back to Earth's earliest life forms. The time frame that elements spend in different reservoirs varies dramatically. Carbon may circulate through the atmosphere for centuries, reside in the oceans for thousands of years, or remain locked in rock formations for millions. This creates a fascinating temporal dimension to element cycling. The calcium in your bones might have been part of a Tyrannosaurus rex 65 million years ago, a trilobite 400 million years ago, or perhaps even part of an ancient sea creature whose body formed limestone that would later be weathered and absorbed by plants that you eventually consumed. Nitrogen follows a similar cyclical path. When your body decomposes, the nitrogen in your proteins returns to the soil, where bacteria transform it through processes like nitrification and denitrification. This makes nitrogen available for plants, which incorporate it into their tissues. The same nitrogen atoms that help form your muscles today might help form a tree tomorrow, a mushroom the next century, and perhaps the body of a human being not yet born in the distant future. Phosphorus, crucial for your DNA and cellular energy transfer, also continues its journey after death. Unlike carbon and nitrogen, phosphorus lacks a significant atmospheric component, making its cycle more dependent on geological processes. The phosphorus in your body ultimately returns to soil and water, where it can be incorporated into sediments, later uplifted and weathered from rocks, and eventually taken up by future organisms. This element's journey demonstrates how even the most fundamental components of life participate in cycles that span geological timescales. Every time you exhale, you release carbon dioxide molecules that contain atoms with extraordinary histories. As one researcher noted, the carbon in our breath was once part of ancient plants, dinosaurs, and other humans, illustrating the continuous cycling of elements. This statement captures a profound scientific reality. The carbon dioxide you just exhaled might contain carbon atoms that were once part of Julius Caesar's body, a prehistoric mammoth, or the first plants that colonized land hundreds of millions of years ago. With each breath, you participate in a planetary exchange that has continued uninterrupted for billions of years. Human activities have dramatically altered these natural cycles in recent decades. Mining operations extract elements from deep geological reservoirs at rates far exceeding natural processes. Agricultural practices, particularly fertilizer use, have more than doubled the amount of available nitrogen and phosphorus entering ecosystems. The burning of fossil fuels has released carbon that was sequestered for millions of years, increasing atmospheric carbon dioxide to unprecedented levels. These disruptions reveal our profound influence on ancient cycles that maintain Earth's delicate balance. In the very distant future, as our sun depletes its nuclear fuel and expands into a red giant approximately 5 billion years from now, Earth's fate will change dramatically. The sun will grow large enough to engulf the inner planets, including ours. This cosmic event will disperse Earth's elements, including those that have cycled through countless organisms, back into space, potentially becoming part of new stars, planets, and perhaps even new forms of life. The atoms in your body are essentially immortal, far outlasting the temporary arrangements they form in your tissues. Death, from this perspective, isn't an ending but a transition, a release of stellar elements back into Earth cycles, where they continue their journey through geological and biological systems. The hydrogen, carbon, nitrogen, oxygen, and other elements that currently constitute your body will exist long after your consciousness has ceased, participating in the same natural cycles that have sustained life for billions of years. This understanding transforms how we might view our own mortality. While our individual consciousness may be finite, the physical building blocks that make us who we are will continue their cosmic journey indefinitely. In a very real sense, parts of us will become flowers and trees, soil and ocean creatures, and perhaps even other human beings in the distant future. We are temporary participants in an eternal process, borrowing stellar elements for a brief moment before returning them to the grand cycle from which they came. Cosmic perspective, the philosophical implications. This cosmic revelation about our stellar heritage shakes our very understanding of existence. When you wake up each morning, brush your teeth, and go about your daily life, there's a profound disconnect between that mundane experience and the extraordinary cosmic processes that made your consciousness possible. The atoms flowing through your neural pathways, enabling you to comprehend these words, emerge from stellar furnaces that burned billions of years before Earth even existed. In cosmic terms, we are infinitesimal, brief flickers of awareness on a tiny planet orbiting an ordinary star in one galaxy among trillions. Yet simultaneously, we are extraordinary arrangements of matter capable of contemplating our own origins. We are, as far as we know, one of the rare ways the universe has organized star-forged elements in a patterns complex enough to study themselves. The tension between cosmic insignificance and conscious significance offers a framework for understanding our place in the cosmos. We are neither the center of creation nor merely accidental byproducts, but conscious manifestations of a universe reaching for self-knowledge through the elements it created. Throughout human history, cultures have intuited this deep connection to the cosmos. Ancient Egyptians saw the stars as manifestations of their gods and believed human souls would join them after death. Indigenous Australian traditions speak of the Seven Sisters constellation as ancestral beings who shaped the landscape. Mesoamerican civilizations meticulously tracked celestial movements, weaving cosmic cycles into their cultural fabric. These ancient perspectives represent humanity's enduring sense of cosmic belonging, a connection modern science has now confirmed with precise data. Modern science transformed these mythological connections into verifiable fact through the discovery of stellar nucleosynthesis. We are made of star stuff, Carl Sagan famously articulated, a powerful distillation of complex astrophysics that resonates because it speaks to something we've always sensed about our cosmic heritage. This knowledge connects us to the stars and to every living organism on Earth. The carbon in a redwood tree, the oxygen in a dolphin's bloodstream, the nitrogen in a butterfly's wings, all share the same stellar ancestry as the elements in your body. This atomic kinship runs deeper than biological evolution. It's written in the very substance of all terrestrial life. The atoms in your left hand might have originated in an entirely different star than those in your right. You're a composite of multiple stellar deaths spanning billions of years. The iron atoms in your blood may have been forged in a star that exploded before our solar system existed, while carbon atoms in your skin cells might have emerged from an entirely different stellar source. Your body is a living museum of cosmic history. It contains hydrogen atoms created in the Big Bang, carbon atoms from aging stars, and heavier elements from supernova explosions. Every atom tells a story of cosmic evolution spanning the entire history of the universe. You are 13.8 billion years in the making. Perhaps the most profound implication of our stellar heritage is how it reframes consciousness itself. The universe has organized its own matter into patterns complex enough to contemplate its own existence. As Neil deGrasse Tyson puts it, we are not just in the universe. We are the universe, a way for it to know itself. This perspective transforms our approach to environmental ethics. Recognizing that the elements cycling through living systems emerge from the same stellar sources as those in our bodies dissolves the artificial boundary between human and nature. Environmental protection becomes about acknowledging the shared cosmic heritage of all matter on Earth. Similarly, our understanding of human connection deepens. The atoms that make up your body and mind have existed since nearly the beginning of time and will outlast your individual consciousness by billions of years. They are borrowed temporarily from the cosmic inventory, arranged briefly into the pattern you call self before returning to Earth cycles. This knowledge contextualizes human individuality within a greater whole. The perspective also offers a framework for existential meaning that transcends traditional religious or secular approaches. The scientific fact of our stellar origins provides a factual foundation for cosmic belonging. We are integral participants in the universe's ongoing evolution, temporary arrangements of ancient atoms engaged in the extraordinary act of conscious existence. Recognizing our stellar heritage enables a profound shift in worldview. We move from seeing ourselves as isolated biological entities to understanding ourselves as conscious manifestations of a 13.8 billion year cosmic process. Our individual lives become moments in an unbroken chain of cosmic evolution stretching from the Big Bang through stellar formation to conscious reflection. This perspective doesn't eliminate the value of individual human experiences, love, creativity, suffering, joy, but situates them within a cosmic context that adds depth to even the most personal moments. When you experience the birth of a child, you're witnessing the latest arrangement of stellar elements into a new conscious entity. When you create art, you're using star-forged matter to express meaning. Understanding our cosmic origins isn't just accumulating scientific facts, but discovering the most profound origin story we've ever found, Carl Sagan emphasized. Unlike mythological narratives that placed humans at the center, this science-based story reveals our deep interconnection with all cosmic processes. It doesn't diminish humanity, but expands our understanding of what being human means. Embracing this cosmic perspective doesn't require abandoning other sources of meaning, religious, philosophical, or cultural. It provides a factual foundation upon which diverse interpretations can build. Whether you see cosmic evolution as evidence of divine creation, emergent complexity, or simply physical law, the shared reality of our stellar origins offers common ground for dialogue about humanity's place in the cosmos. We are not merely temporary visitors in the universe. We are manifestations of the cosmic process itself. As Dr. Alexis Quintana noted, supernovae act as both creators and destroyers, dispersing the building blocks that eventually form conscious beings. This realization transforms our self-perception from isolated individuals to vital threads in the universal tapestry. Each of us represents the universe achieving consciousness through its own stellar products. When darkness falls and stellar light reaches your eyes, you're witnessing your own origins. It's a reunion across space-time. The stars and you, the created and creator, linked in an eternal cosmic dance.